Okay, so hi all, and welcome to this second video, the Wednesday video for this week, where we will, or mostly I'll spend the better part of this time just doing one really awful example from start to finish. And by awful, of course, I just mean everything that could go wrong will go wrong in this, so that I can show you the worst of the situation, show you all the things that you might encounter in homework problems. But I don't think you see anything quite so bad, at least not all in one place. But anyway, we'll do one big example to show you all of the tricks in action. So I'll just give you the very quick recap of our two strategies from the last video, which we'll use in one mega example today. So when we're trying to do these inverse Laplace transforms, right? Doing the forward transform is pretty straightforward. So when we have an ODE, we take the Laplace of both sides. That's usually pretty quick and pretty painless because it's just reading the chart for the most part. Organizing it to read Laplace of y equals, that's pretty easy also, right? So in our strategy, where was that here? So this is easy, step one. Step two is pretty easy, just rearranging some stuff to make it read Laplace of y equals. Okay, it's step three that's the hard part, this last step where I say, now let me take each of these terms and do the inverse transform, which means I'm going to try to read the chart from right to left instead of left to right. And of course, mostly the reason why it's hard is because our chart is there aren't that many options. So of course, in life and in ODEs, I don't know. I could in theory end up with anything over here. And I have to somehow make these things over here, I have to make them look like things in the right column of the chart so that I could read the chart to the left and get an answer. Well, that's tough, right? We've used charts before, for derivatives and integrals, maybe in calculus, and you have to kind of get everything lined up just right, otherwise it doesn't work. So similarly for us, when I'm doing these inverse transforms, I have to get them lined up just right to match the chart. So what we looked at in the last video were two tricks. For doing that, one, partial fractions. So most of the time when we look at our chart, first of all of the things in the right column are fractions. And for the most part, they're fractions of polynomials. Just, something in the top, a polynomial in the top, and a polynomial in the bottom. So how do we, if we already see the thing that we're working with in the chart, great. You could just use it directly and you're good to go. But most of the time, the interesting problems, you don't exactly have what you're looking for, and you have to do a little bit of creative algebra-ing, I guess, in order to put it in the right format. So one trick is partial fractions. So if you see something, you see a fraction, and the polynomial that's on the bottom, you can factor it into two pieces. Then you can split it into something over the first piece plus something over the second piece. And you have to do some algebra, basically an undetermined coefficients kind of thing, in order to figure out what P1 and P2 are up here. But the benefit of doing that is that then hopefully Q1 and Q2 are both things you see in the chart, and you maybe have to do a little bit of fudging on the top to make it match the numerator. But the denominator is always the thing that we're most concerned with and fixated on. So don't really worry about the numerators. Just focus on the denominators. So that's one trick, and we did an example of that. Our second trick is that what happens when you can't factor. So completing the square is the sort of backup plan. That if you can't factor, like you do for partial fractions, then we do this complete the square thing where we rewrite something that looks like this into something that looks like this in the circle here. And the benefit of that is that this is perfect. This is exactly the denominator for rules 6 and 7. So as long as you can write it like this, which you always can, you'll be able to, again, maybe with some massaging on the numerator side, you're going to be able to use rules 6 and 10 if you complete, 6 and 7 if you complete the square. And we did an example of that. So I finished with this sort of overview then, say, okay, so I start with some fraction, polynomial top, polynomial bottom. What do I do? First, second, third, and so on. So the first thing to do is if you can factor Q, do it. So if I can factor the bottom, factor it, and then split it with partial fractions. And if each of the two pieces that you end up with are things you can then work with and do the inverse of, you're done. Okay. Now it's possible that Q doesn't factor, which is what we did in the last example. So if Q doesn't factor, then complete the square on Q, And then hopefully, whatever you see, you can use the chart for, and you're done. And that's what we saw in the last example. But unfortunately, we might sometimes be in case 2b here, which is where you do partial fractions because this factors, but then one or some of the terms that you get from partial fractions, they themselves are going to need a complete the square treatment. So I'm going to do an example of this so that you can see the sort of everything that you might have to do in a problem. And there's a little bit of an art or a little bit of maybe timing to getting it just right. So let's take a look at one. Okay, so now we've been chickening out a little bit, and our first couple of examples have been homogeneous. In other words, we've added 0 over here. So naturally, as you might imagine, when you do a non-homogeneous, which of course is what this is, you're going to probably end up with something a little uglier, which we most certainly are. So this is going to be a little trickier because I have a cosine over here. But okay, but we'll try, right? We'll do it. All right, so away we go. So we take the transform of both sides, and we see what happens. So if I do the transform of y double prime, I get s squared Laplace of y minus s times y of 0, that's 1, minus y prime of 0, that's 0. All right, so that's the Laplace of y double prime. And then I have 2, negative 2, times, and then the Laplace of y prime is s Laplace of y minus y of 0. And then I have plus 2 Laplace of y for the third term. And now we've been getting away with that in our first couple of examples, but sadly, the right-hand side is not 0, it's cosine of t, which I got to look that one up in the chart. And if you do, the transform of cosine of t is s over s squared plus 1. So I got it. So I got that. All right, so that's the whole transform done. So step 1, I guess, right? I've done the forward transform of everybody. Now I got to make this read Laplace of y equals. Okay, that's not too hard. I'm going to do my usual grouping. So I have s squared and minus 2s and plus 2. Those things have Laplace of y's, so let's put those together. And what doesn't have a Laplace of y? Let's see. So I have minus s, and that looks like a plus 2 over here. So those things I'm going to throw to the other side. Now there was already this over here, s over s squared plus 1, so don't forget, that's already over here. But now I'm going to move the s over, so I get plus s, and this is a plus 2 on the left, which would make it a negative 2 on the right. Okay, so I'm going to point out one thing here, which is that in some algebra contexts, I guess, I would maybe want to actually put these together as one mega fraction. In other words, put this over s squared plus 1 and combine stuff. But unfortunately, if you do that, you're going to end up with, number one, you're going to end up with an s cubed on top, which I don't really want to have the top be bigger than the bottom in exponent. And also, these aren't really naturally the same type. Now, I mean, if I had that, sure, I would combine those, because that would be silly not to, because they're already the same type of thing. But if I don't have things of the same type, I think in this case, you're better off actually leaving them alone, because what would end up happening is we'd end up splitting it up later anyway. So I'm going to leave the right side as is. Okay, now in order to make this read Laplace of y equals, I just have one last step, which is to, of course, divide both sides by s times s squared minus 2s plus 2. So if I do that again, I'm going to keep these fractions separate and say, okay, this one turns into s squared plus 1 over that. All right. And then I will put these two together, though, or just for the sake of not having 3 fractions here. Although there's nothing wrong if you wanted to do 3, you could do 3. But I'm going to list this as s minus 2 over s squared minus 2s plus 2. Okay, so I'll put those two. I'll at least group those two together for now. All right, so here's where we're at. So we have this. So first of all, this is already worse than an example we've done because I have 2 terms over here. Now that's not a crisis, just because you have 2 terms. If both of them, or if each of them is reasonably easy to deal with, then so what? Then you have a few things you're going to look up in the chart, and the answer is still coming very soon. Unfortunately, that's not what I'm concerned about. What I am concerned about is the fact that when I look at these 2 fractions that I have, again, look at the bottom first. I'm hoping to see the bottom in my chart. Well, I most certainly don't have anything that looks like this. And I don't have anything that actually looks like that either. So I'm 0 for 2 in terms of things, in terms of lucking out with things being in my chart. Okay, so now let's appeal to what we said, recapped for you at the beginning today. If you have a fraction of polynomials, which each of these is a fraction of polynomials, I probably want to start doing our tricks in order to split them up, to make them a little more digestible and rewriting and all that. So I look at the first one, and I look at the bottom, and the bottom is already factored into something times something. So I know that that's screaming for us to do, hopefully it's screaming to you, to do partial fractions, because that's going to at least help me split this into two pieces. One of them will be over s squared plus 1, and then one of them will be over s squared minus 2s plus 2. Now, once I split this, I'm going to have something over this guy, but then this is also over the same character. So I might be able to put those together at least, and then maybe some good things will happen. So I'm trying to just be you here for a minute and say, how do you know what to do right now? Well, I don't know. I mean, I'm looking at these two fractions. This one's saying partial fraction me because I have two factors in the bottom. What's this one saying? Well, s squared minus 2s plus 2, that doesn't factor. You could try it for a minute, but it doesn't factor. So probably this is going to need to complete the square. Remember, that's our other method, is if you can't factor something, probably completing the square is a good idea. So I don't know that it necessarily matters a whole lot what order, in this case, that we do these in. Well, it does. So I guess I would say don't complete the square until the end, because it just ends up making algebra a little more complicated. Completing the square is more of a stylistic thing anyway, whereas partial fractions are actually physically breaking something down and changing it into something new. So do the harder thing first. So let's do partial fractions first. So I'm going to do partial fractions. And I'm going to run out of space on this slide, so I'm going to set it up here, but I'll go on to the next slide. And I'm going to propose that this can be rewritten in our usual partial fraction trick. So we say that's going to be written as something over s squared plus 1 and something over s squared minus 2s plus 2. Okay, and now our trick says whatever is in the bottom, I should guess for the top a polynomial of degree 1 less than the bottom. So in this case, both of these bottoms have squareds. So on top, I need a first degree, or which is of course the equation of a line. So I'll do as plus b, and maybe cs plus d. So already this is going to get a little messy because now I have 4 unknown coefficients, a, b, c, d. So I am going to have to do a little bit of rigorous algebra here in order to figure out who a, b, c, d are. Okay, I'll do this one out just so that I can show you a bad one to completion. I'm not sure that you have anything quite this awful in your future, but let me do it. So of course the trick for partial fractions is that in order to, this is a guess right now that I've written down. So in order to make the guess work, I have to get a common denominator, which of course is just the product of these two, right? So it'll match this one over here. And what does this one need? This one needs this guy, and this one needs this guy. So I'm essentially just sort of, you could say I'm cross-multiplying in some sense. And the numerators have to line up. So over here I just have a simple s, and I'm going to get a whole mess of stuff over here. So for this I need to go to the new slide though. So what happens when I combine these is that on the left-hand side I get just plain old s, and on the right-hand side I get quite an algebra problem. I'm going to take the numerator of the first one times the denominator of the second one, and then take the denominator of the second one times the numerator of the first one. Right? In essence, it's a cross multiply, right? But I'm getting a common denominator. And that has to equal the numerator of the left-hand side, which is just s. Okay, now unfortunately, I don't know of any slick way to do this other than to just multiply this all out. Right? Ugh. All right, this is where it's a little gross. But in order to multiply this out, this is like an extended FOIL. This is, I have to take as and hit it to each of the 3, and then I have to take b and hit it with each of the 3. So just be sort of careful here. When I do as times each of them, I get as cubed. I get minus 2as squareds and 2as's. Right, so that's me doing as to each of these 3. And now if I do b to each of these 3, I get bs squared minus 2bs plus 2b. All So you get all six. You get 6 terms for the first pair. Now the second pair is just a regular FOIL. So that's CS cubed and DS squared and CS and D. All right. Sorry, DS squared. Okay, so now in order to do matching, I have to get powers of S. It's best to organize ourselves in that fashion. So let me do the S cubes first, which I have A plus C. And then how about the S squareds? I have negative 2A and B and D. And then the S's, I have 2A minus 2B plus C. And then the number pieces, I have 2B plus D. Okay, I'm just double checking with my side work here to make sure this agrees. Yes, okay, so I think we're good. Now, to do matching, I have to match powers of S. So now notice on the left, I only have an S. I have 1 times S. I don't have any S cubes. I don't have any S squareds. And I don't have any just number pieces. I do have an S term, and the coefficient of that needs to be 1. So there are my 4 equations and 4 unknowns. So I'll write them down for you down here. So I end up with 0 equals A plus C. Maybe I'll keep the number on the right side, actually. So not that it really matters, but I'll say A plus C equals 0. The second fact I have is negative 2A plus B plus D equals 0. The third one is 2A minus 2B plus C equals 1. And the last one is 2B plus D equals 0. So sometimes you get a little bit lucky when you have these systems that there's maybe something clever that you notice to be able to kind of, put these together. I don't think there's anything particularly great about these. So my advice for these is to take the easiest ones, which would be the first and the last one, and just use these to do a substitution. So this one I might write as C equals negative A. And this one I might write as D equals negative 2B. And then these substitutions, so C and D, if I plug in what they equal in terms of A and B into the middle two, I'll just have 2 equations with A and B. So that'll be a good way to finish this thing. So this one I'm going to say, let me rewrite this one as negative 2A plus B. So I only want A's and B's. So instead of D, I'm going to write negative 2B. And this one, same idea. I'm going to use the top one. So I'm going to say that's 2A minus 2B. So A and B are okay, but I don't want a C. So how about I do minus A? And that equals 1. That's me taking this one and putting it in here. Okay, now the good news is that these two that are left now are both just A's and B's. So I'll be able to get an answer momentarily. So this one turns into negative 2A minus B equals 0. And the second one turns into, let's see, I got A minus 2B equals 1. All right, and now I'm down to a more familiar problem that I can solve via our usual, or whatever your favorite way is. I'm going to double the bottom one and add. So if I double the bottom one and add, I end up with negative 5b equals 2, which tells me b is negative 2/5. And once you get one of them, you can usually unravel all of them pretty quickly now. So that's 1 out of 4. That, of course, tells me also now d is 4/5. Right, if b is negative 2/5. Let's see, I can use B to also tell me about A. So this would say negative 2A plus 2/5 equals 0. So So I think that means A is 1/5. And then lastly, if A is 1/5, then C is negative 1/5. Okay, so that's a little bit of work, obviously, to get the algebra to tell you what A, B, C, D are, and they're all fractions, which is just great. But okay, that's fine, I guess. So let me put everybody in their place, and we'll recap with where we are with our problem. So far, I've just worked with this one, right? I didn't even touch this one yet. But I have now successfully split this into these two pieces. I now know A, B, C, D. So I'm going to say Laplace of y equals these two pieces, and then plus this third one. And then we'll do some simplifying. All right, so pulling all of this together, I have Laplace of y equals. Okay, so now I think if I put in my A, and B is negative 2/5, that's over s squared plus 1. And then C is negative 1/5 s plus D, which is 4/5. That's over s squared minus 2s plus 2. And then I had an original term already over here, right? S minus 2 over s squared minus 2s plus 2. Okay, so I think I've reunited with the original problem, which is now fully in front of us here. Okay, so at this point, I want to check in to see, am I heading in a good place, or am I heading down a bad path, I guess. So mostly I'm looking at the denominators. I'll worry about the numerators at the end. So s squared plus 1, that's good. S squared plus 1 is actually in the chart. It's in rules 4 and 5 for cosine and or sine. So that's pretty good. So in terms of my happiness level, I'm happy with that bottom. Now, I notice over here, first of all, these are actually the same on the bottom. So I'm going to put the tops together. So I'll do that in a second, I guess. But if I look at the bottom, neither of these is particular. I mean, they're the same, right? But this is not particularly good, right? I don't see this in the chart. And just like we've always said, if you have a fraction of polynomials, which we do, if you could factor the bottom, you should factor it so you could split it up. But I can't factor the bottom here. And so, of course, the idea is that when you can't factor, is we're going to do a complete the square. And we're going to do it on this piece. So, I think my best advice for you in terms of complete the square is to just write out your goal, which is I want to try to make it look like rules 6 and 7. So I want to try to make it look like s minus a squared plus b squared, and then just remind yourself, well, what it has to be true. Well, if you FOIL this, you get s squared minus 2as plus a squared plus b squared. Okay. Well, the s squareds line up already, so check. That has to match that, which tells me immediately that a is 1. And this has to match this. Well, if a is 1, then of course that means b squared is also 1. I think this is the same one that we did maybe in a previous example, so I don't want you to always think that they're both 1, but in this case they happen to both turn out to be 1. Okay, so that's going to be a cosmetic thing, that rather than writing s squared minus 2s plus 2, I could write s minus 1 squared plus 1, which is in the chart. All right? So I'm going to do a couple of things. I don't want to overwhelm you with things all at once, so let me just write this down as is. So one thing I should do first, probably before I do the complete the square, is that these are the same. So now is when I certainly do want to write this as one fraction. Right? There's no point of having some of these here and some of them over here, because I don't think the top, I mean, this is not already perfect for the chart anyway. So let me at least combine the tops, and then we can deal with the disaster that maybe is going to happen there. So if I combine the tops, which I'm adding, so I have negative 1/5 and 1s, which I'm pretty sure that's 4/5. Yes. And then what else do I have? I have 4/5 minus 2. I think that's minus 6/5. All right, so I'm already sick of the fifths that I see happening here, but that's all right. And now the bottom, I could say this, so write this down if you want, or don't. I could say that, because, right, all I do is combine these two fractions. But we just got finished over here saying that s squared minus 2s plus 2 is going to more friendlierly, that's not a word, be written as s minus 1 squared. That's my complete the square. Right? So where did that come from? It came from us doing complete the square. Okay, so we're making progress, even though this is still a bit of a hot mess right now. So now the bottoms are both, so let me be you for a minute, right? So bottom, good. Because by good, I mean it's in the chart. This bottom, good. It's also in the chart. Okay, so when you get to the point in these problems where the bottoms are all happy, now you want to look to the top and say, now let me try to fix the top. The top is always way easier to fix. We're going to have to do a little bit of trickery here. But I can always adjust the top to be whatever I need it to be. Okay, so put that on hold for a second, and I'm going to pull up the chart so that we can take a quick peek at it. So, all right, so of course I'm going for, so look at, you have this all in front of you, hopefully. So on our sheet now, we have an s squared plus 1 term. That's perfect for 4 and 5, s squared plus 1. But of course on the top, I'm going to need to either have a number 1 or just a nice s, just an s. So keep that in mind, right? S squared plus 1 on the bottom is great, but you need to either have a 1 or an s on top. Similarly, I have these two, 6 and 7. I have s minus 1 squared plus 1 squared. So I have those are perfect, but the top needs to either be 1 or s minus 1. Because remember, a and b for us both happen to be 1. So this is where we have to make it match the chart. The bottom is perfect, so I'm not going to touch the bottoms. But the tops now have to match the 4 tops that I see here. So try to keep these in mind, or if you have the chart printed out, keep it next to you. And that's motivating what we're about to do in this step. Okay, let's do the easier one first. So s squared plus 1, great. But the top has to be just s or just 1. Nowhere am I allowed to have some s's minus something else. So right off the bat, I can't have subtraction. I can't have 2 terms in the top. But algebraically, why is this easy to fix? Because you can always split fractions that way. Right? You can't do it when it's the reciprocal. But when I have 2 terms on top and 1 on the bottom, right? I can split this up and say that this is 1/5 s over s squared plus 1. Oops, lost it. And then minus 2/5 s. Oh, that's no s there, right? Minus 2/5 over s squared plus 1. Sorry. All right, so I can certainly say that, right? There's no trick there. That's just algebra. And let me keep going on these two before we tackle the other one. Now, what did we say? You can have just s on top, or you could have just 1 on top. Oh, well, crap. I have neither of those things true. Oh, but wait a minute. Yes, I do. Because 1/5 is just a constant. It's just a multiplier. So pull that out in front. 2/5, that's just a multiplier. Pull that out in front. And voila, these are both perfect for the chart. Remember, I'm never afraid of numbers, coefficients in front. Those are always just going to come along at the end anyway. But this is absolutely like a double check, right? Those are both absolutely perfect. They are in the chart. So I'm done with those. I mean, I got to do it, but I'm ready for those. Okay. Now, other piece is a little trickier. So looking back at the chart one more time, I'm allowed to have s minus 1, or I'm allowed to have a 1 on top. Now, in this case, I would not want to do, I mean, it wouldn't maybe be the worst thing, but if I do the same thing we just did, The only reason why I'm not super happy about that is that I actually do want s minus 1 on top. I don't want just s. So what I'm going to do here is I'm going to try to be a little crafty with engineering an s minus 1 on top. Now, I'm not super jazzed about it in this format, so you can go about this any way you want. I don't even have an s by itself. This 4/5 is maybe the thing that's bothering me the most. So since I don't want that in particular, how about I factor that out? Oop. So this is the great equalizer, right? When you don't like something, if you just pull it out in front, at least that kind of pushes it away, and maybe things are in a better format now for you to look at it. So if I factor out 4/5, that leaves me with just an s. Now here's where you have to put your brain on, though, for a second. If you factor out 4/5 from 6/5, which is probably not something that you really do every day, you have to sort of ask yourself, well, what are you doing when you factor something out? It's that you're dividing by what you're pulling out, right? I mean, I had 4/5 here, and I divided by 4/5, and that's how I ended up with 1. So when I have 6/5, if I divide 6/5 by 4/5, that's just 6/4. I'll write it that way so you can sort of see where that comes from. Okay, let that roll around in your head for a minute, but that's just literally third grade math. But think about it for a second. But I think that's right. You could always just double check, right? If I distributed 4/5 and I did 4/5 times 6/4, isn't it true that I get 6/5? Sure I do. Right. Okay. So that's all right. Now I didn't quite get s minus 1. I got s minus, what 6/4 is also known as 1.5. So let's do the easiest thing ever, which is to say, you didn't really want that. You wanted s minus 1. Okay, that's fine. But you really had that. So now I'm going to group those together and those together. All right, sorry, I don't know why that looks all weird. Let me do one more. All right, so 6/4 is 1.5. So that's 1 with an extra half left over. Right, s minus 1 squared plus 1. Okay, right? So now I'm going to split this up in the same way that we did it over here. I'm going to say, because I'm very happy with that, I'm less happy with what's about to be over here, but that's all right. I can fix that at the very last step. All right? So I'm just going to go to the last slide. I swear this is the end of the problem. So I'm going to split this guy, so let me write this all down one more time. Laplace of y equals. So I have 1/5 s over s squared plus 1, and 2/5 1 over s squared plus 1. Okay, those are both good. Now this I'm splitting into two pieces, so they both have a 4/5 out in front though. So 4/5 s minus 1 over that. Alright, and then who's left over? I gotta just be careful here. So I have 4/5, negative 1/2 on top. Okay. Okay, so these were both already excellent. Good, good. We can at least join one more into the yes, yes club, that the both top and bottom are perfectly in the chart. Whew. Now, this is the easiest one of all to fix. The last one's almost good. The bottom is good, but the top is still not great. And by that I mean we were hoping to have a 1 up there. Because, right, I have to match, that's b squared, which obviously means b is 1. You need a 1 up there. Oh, well, this is the easiest fix ever. Just move this negative 1/2 into the front. So I'm going to save myself the anguish of writing this again, and I'm going to cheat here and say, instead of 4/5 times negative 1/2, or with a negative 1/2 there, if I do negative 1/2 times 4/5, I'm pretty sure that that's negative, I'll do 4/10. How about that? So that you can see that it came from doing negative 1/2 times the 4/5 that was already there. Of course, that's really just negative 2/5. But we'll write that in the next line. And now this one is also perfect. Whew. Okay, so this is what I mean when I said this was pretty terrible. But these are all in the correct format now to finally end this problem. I'll give us a nice big space here. So each of these is now good to go. Coefficients just come along. This is number 3. I don't remember. I think I wrote it down on my little page here. I'm sorry, that's 5. Okay, sorry, that's number 5 in the chart, which is cosine. All right, 2/5, that comes along. And now this one is number 4, and that's sine. Sorry, I don't know why this is looking weird. Okay. This one's good too, so I have 4/5, and this is in my chart 7, I think, if I wrote it down correctly on my sheet here. This is rule number 7 in the chart, which is e with cosine, so that's e to the at cosine of bt. In this example, a and b both happen to be 1. So, and then the last one, this is driving me crazy, that's really negative 2/5, right? 4/10. So I have minus 2/5. And then this one is, this is rule number 6, which is e to the at sine of bt. And that is the answer. Whew. So deep breath, right? So that was obviously a doozy. That's probably, I don't know where we are, half an hour or closer to 40 minutes into this problem. Now, that was with me doing an awful lot of talking, but as I said, right, I don't know that you see any that actually involve you having to do all of these terrible things all in one problem. But you might have to do some of these things in each problem, kind of a situation. Let me at least point out, though, before we move on, that if we had solved this the old way, we would have gotten a homogeneous. So remember, it's been so long since we started this problem. Here was the original ODE up here. Now this you would have done a homogeneous solution, and then you would have used one of our techniques, probably undetermined coefficients maybe, to get one non-homogeneous solution. And at the end, you would have crammed them together. You would have put a C1, C2 in front of the homogeneous piece. And then you would have used these 2 points, which, to be honest, is kind of a disaster. Well, I don't want to say disaster, but having to do these, you'd have a really awful algebra situation on your hands. Not that we didn't have many awful algebra problems in this last 30 minutes, but this is no picnic, right? But I would have ended up with a homogeneous solution plus a non-homogeneous solution. But look actually what we ended up with. If you squint at this hard enough, maybe you can see that this should look a little bit familiar. That's our old friend. That's the homogeneous solution. Remember, that's our complex roots case, where we got e with cosine and e with sine. That was our old homogeneous. And what must that have been? That must have been the non-homogeneous solution, which would have maybe been attained by undetermined coefficients or variation of parameters. So not only do you get the actual same solution, you actually even get the same sort of pieces. This would have been C1 and C2. 1/5 and 2/5 would have come out of doing the either undetermined coefficients. Those would have been your A and B, I guess. Or they would have maybe come out of variation of parameters from doing U1 and U2. Okay, so you do still, this is, I promise, the same answer that you would have gotten doing it the other way. Now, stylistically, I don't know, right? If you'd rather have done it that way and I didn't say, and somebody didn't tell you, oh, you got to do it one way or the other, I might have chosen some of our previous methods as well. But anyway, but this is good to see, right? Good to see sort of everything that could go wrong in one problem, and that it does turn out at the end to be a familiar solution. Okay, so that's kind of the end of that. I am going to use the last 10 minutes, though, to just quickly... so I think we've done 1 through 5 and used them quite regularly. And 6 and 7 now, we've done some examples with those. We haven't used 8, so let me at least just write 8 down for you and sort of do a little brief discussion on 8. So what does 8 say? 8 is just a generalized version of 6 and 7, which says if you have e to something and then a function, you can do the transform. Remember, big F, that's the transform of little f. You can do the transform of little f, but then instead of just doing f of s, you just shift it by c. So what is having an e in front of it? All it does is shift your answer. So when do we use this? Right, so just to talk about this a little bit. So so from the chart, we have number 8 says that if you have e to the ct times some function, then the transform of that is actually just big F of s minus c. Where as usual, big F is the transform of little f. But notice it's not big F of s. It's big F of s, but with s minus c, whatever this number is. C is a number. Maybe it's f of s minus 5. Okay. So the point is that this is a very easy rule to use, because all you really have to do is just do the regular big F, and then shift your answer. So it's not hard. So let me at least show this to you in action here, so you can see how this works. To show that this is true is very easy. Let me just do an example or two of using this, though. But this is, again, just an easy one that you could do the integral definition and see that you get this. But let's see this in action, since this will be a good preview of what we'll do in the next video. So, for example, if I just take a nice, easy, simple question like this, what's the transform of e to the 5t times t squared, let's say? Okay, then obviously this looks just like this rule, where obviously c is 5, and little f of t is t squared. Now, I encourage you to not be too fast with this. I might say to myself, all right, so in order to match this up with the rule, obviously, first thing I might notice is that c is 5. And the other thing that I might notice is that f of t, give myself a little more space here, is t squared. Now, if f of t is t squared, you know big F of s, because you can just use the chart. So this is rule number 3, I think, in the chart. It says t to some power. If you transform that, you get s. Oh gosh, I always forget this one. Oh, I wrote it down. You get the same thing, and then, okay, a plus 1 factorial on the bottom. Okay, so I get s squared over 3 factorial, which is 6, right? We all know factorial, right? It just means multiply all the numbers less than or equal to yourself. So 3 factorial is 3 times 2 times 1. So that's 6. Oh, I have this upside down. Do I have it upside down? Oh gosh, I'm so sorry. I'm sorry. I should have just looked at the chart. Sorry about that. Erase all that. So it should be, it's whatever the exponent is. It's, oh right, okay, I'm sorry. It's t to the 2 is 2 factorial over s. That's the one that's plus 1 over s cubed. Sorry about that. 2 factorial is just 2 times 1. So that's just 2 over s cubed. Now that's not the answer, right? So here's how you get an easy question wrong on the exam, is that that's f of s, so that's big F of s. But remember, the answer is supposed to be big F of s minus c. So I have all the pieces here, right? I know that, and I know that. So now I'm ready to do the transform. And it's big F of s minus 5. And that's what c is, 5. But what is that? Well, big F of s is 2 over s cubed. So big F of s minus 5, it kind of helps to say it fast, would be 2 over s minus 5 cubed. And that's the answer. Okay? So you have to do the shift, otherwise, well, you're not really honoring the rule here. And this is going to come into play with step functions and things that we're going to do in the next video. But, okay, so that's the forward. So if you see something like this, you have an e in front of a function. This is easy, right? This took me 2 minutes to do, or less if I wasn't talking so much. Right? So it's simple. And even in reverse, it's not too bad. So I'm going to just do one last example. I'm just going to give myself a... okay, I think I can fit it in here. Let's say we want to do the inverse transform. As we know from doing our examples, the inverse transform is the one that's harder, right? The forward one is actually pretty simple. So how about it, right? So let's do the inverse transform of, maybe we have something like 12 over s plus 2 to the 4th. Okay, so if I try to do, anytime I'm doing an inverse transform, I'm looking in the chart, and I'm hoping to see whatever I'm looking at in the right column of the chart. Well, we're going to add one new trick to our repertoire, which is to say, if you see something in the chart, or if what you're looking at is something in the chart, but it's shifted, that's what this minus 5 or minus c here means, means you've just moved it over, then that's going to be every bit as good as having the thing you actually want. So by that I mean, if you look at this, right, and this is where you have to have a little bit of instinct, I guess, or thoughts here. If you look at, if this, instead of being shifted by 2, if this was just s to the 4th, s to the 4th with something on top is definitely in the chart. So if I say, well, this kind of looks like this might have just been shifted over by 2. So if I propose that big F of s minus 2 might be this. And what does this tell me about big F of s? Oh, I'm sorry. Why did I say minus? Plus 2. I'm sorry about that. Right? This looks like it's this, right? This looks like s plus 2. Sorry. This looks like s plus 2 has been plugged into 12 over s to the 4th, right? That's just sort of you noticing, hopefully, that the bottom looks like s to the 4th. It just has an s plus 2 plugged in. But if that was if that was true, could I do 12 over s to the 4th? Almost. S to the 4th would be good. But if I'm looking at my chart, I would have really liked a 3 factorial, which is 6. So how about I do that? Because if that's right, so all I did is I just rewrote 12 as 2 times 6. But that now tells me f of t, if I do the inverse, that's invertible. That one's in my chart. I'd get 2, and that's t cubed. So I got all the pieces now. So I'm ready to do the inverse transform of this, so this was realized as big F of s plus 2, and the little f that went with that big F is this one. So if I go backwards now, this is e to the, now here's where I have to write, this was s minus c, so c must be negative 2. Right, that would tell me c is negative 2. Times little f. And that would be the answer. Okay, we'll do some others actually using this shifting thing once we get to the main shifters, which are, I forget what numbers they are. The next grouping, the next 3 in the chart, are all about shifting and turning things off and on and stuff like that. So we'll get to those in the next video. Okay, so for sure you have plenty now, and more than enough examples and situations and all that to complete the homework for this week. So good luck with that, and I'll be back with one more video this week where we will, like I said, start into that last little section of rules in the chart, the ones in the middle, the ones in the last group. So come back on Friday for that, and I'll post these notes here now because we're finished with this sort of chunk, and I'll start our one last grouping of notes with those on Friday.